Hi everyone, I'm Brad Foley from Penn State University, and I'm going to be talking about physical crustal evolution in the Hadean and Archean. And what we mean by that is how potentially different types of tectonic processes and mantle dynamic processes that might have prevailed at this time would have influenced the surface environment and conditions for the origin of life, right? So I'm going to review different kinds of tectonic regimes and processes that might have been occurring on the early Earth, how these different tectonic processes would influence volatile cycling from between surface and interior, and I'll focus mainly on water and CO2 there. How these different types of volatile cycling would influence the state and evolution of the climate and the atmosphere, and also the hydrosphere and the amount of land that might have been exposed during Earth's earliest period of the Hadean and Archean. All right, so we saw from some of the earlier talks in this workshop that very early in Earth's history, after the planet formed and potentially really capped off by the moon forming impact, there was probably a magma ocean state that prevailed where a large section, maybe even the entire mantle, was molten at one point in time. Right, and so since this is important for setting the stage for the later evolution of the solid Earth, right, and the solid mantle, I thought it'd be important to go through some of the definitions and a little bit about how a magma ocean crystallizes and then sets the stage for this later solid interior evolution. Right, so a good way to define a magma ocean would be a layer of the mantle where the melt fraction, right, or percentage of melt present in some melt crystal mixture is large enough for this mixture to overall behave like a liquid, right? And so, one, of course, obvious end member example would be a situation where we have 100% melt and no crystals, right? And of course, that will behave like a liquid, right? But we can have situations in between that, right, where there's some percentage or fraction of crystals within a matrix of liquid magma, right? And it turns out there's a pretty sharp transition point called the rheological transition that separates when one of these melt crystal mixtures will behave like a solid versus behaving like a liquid, right? And it's about 50% crystal fraction, right? So if the crystal fraction is higher than this, right, then the crystals are all in contact with each other. They're pretty tightly, closely packed together, right? And so the only way to get this whole mixture aggregate of crystals and melt to deform, right, is to get the crystals, the solids themselves, to actually deform. All right, so this can happen without too much difficulty at high temperature, high pressure conditions like prevail in Earth's interior, right? Solids can flow and behave like fluids at those conditions, but with a very high effective viscosity, right? So they move very slowly, right? So the viscosity of solids in the mantle interior is going to be something like upwards of 15 orders of magnitude larger than the viscosity of molten magma, right? If the crystal fraction is lower than this rheological transition and we have more melt present, then each crystal can be basically surrounded by melt, right? And in order to get that mixture to flow, all you really need is the melt itself to flow, and it can carry the crystals with it, right? So when we talk about how a magma ocean ends and turns into or solidifies into a solid mantle that will then convect through this solid state deformation and creep process, right? Then we're thinking about a situation where the mantle has everywhere passed this rheological transition, and we have a large enough crystal fraction for the whole thing to behave like a solid rather than like a liquid, right? We think this actually happens, this solidification happens from the bottom or middle up, right, in the mantle, and that's because the temperature profile, right, this solid black line, right, first intersects at the point where crystals first start forming, right, this dotted line, towards the bottom or the middle of the mantle, and then this solidification process then basically propagates up towards the surface. Okay, so after the magma ocean is effectively solidified, right, which remember does not mean that the entire mantle is 100% solid. There will still be some melt present, right, just not enough for the mantle to behave like a liquid, right, in any significant portion of it. Then we can start thinking about tectonic regimes that might have prevailed at this time as a result of mantle convection in the now solidified mantle. All right, so there's basically three main regimes I'm going to highlight here. The first one is the most obvious, right, and that's plate tectonics, like happens today. Right, the plate tectonics, the lithosphere of the Earth, right, which is the layer at the surface where temperatures are cold, right, because it's in contact with this cold atmosphere, and that makes the rocks behave rigidly, right? So this includes the upper portion of the mantle and the crust, right, as part of the lithosphere. And you can think of the lithosphere and the tectonic plates as being one and the same, right? So the lithosphere on Earth with plate tectonics is broken up into these discrete blocks that we call the tectonic plates. They can move with respect to each other, slide past each other, right, collide and converge, spread apart. The plates themselves are rigid, right? Basically non-deforming, and they're separated by very narrow and very weak plate boundaries, right? And that's where all the deformation happens. So you can think of these plate boundaries as sort of the lubrication that allows the plates to move and plate tectonics to happen. Right, one of the real key processes of plate tectonics is subduction, right? This is where the lithosphere, right, is able to dive back down into the mantle interior, right? And the reason this happens is because the lithosphere, being cold, right, is denser than the hotter mantle beneath it, right? And this negative buoyancy drives sinking of plates down into the interior at these regions we call subduction zones. Right? This is important because, one, this is what basically drives most of the plate motions on Earth, right? Plates that are moving the fastest are plates connected to subduction zones being pulled, right, by these heavy, dense sinking slabs as the lithosphere descends down into the mantle interior. Another important thing is this helps drive cycling of volatiles from the surface back into the interior, right? So rocks at the surface that have been interacting with water or other volatiles can then carry some of these volatiles back into the interior. All right, in order to have plate tectonics, we need to be able to form these plate boundaries themselves, right? These regions that are very weak, very narrow, and very rapidly deforming, while the plate interiors remain strong and rigid. We don't know exactly what process or combination of processes actually does this, right? This is one of the biggest unanswered questions in geophysics, and really maybe even in all of solid earth science. And it's something geophysicists have been working on for decades and will probably continue to work on for decades more in the future. Right? You know, we certainly have ideas for how these form. Fracturing and making faults at the surface could be important. Water could be really important for weakening these plate boundaries where two plates are in contact and providing, again, this kind of lubrication that lets plates start moving. Processes happening at the mineral grain scale in rocks could be important. So as you take a rock and shrink the individual mineral grains that make that rock up, that makes the rock weaker, right? And that's something we see happening in a lot of regions in the Earth where shear zones where plates are sliding past each other have been brought up to the surface for us to look at. And then there could be things like shear heating, where as you start shearing a chunk of rock, energy is dissipated that causes the temperature to go up and causes the rock to get weaker, right? So, you know, that's even, that list is incomplete for the various mechanisms that have been proposed for forming these weak plate boundaries. And suffice it to say, we don't know exactly which one or combination of these mechanisms is the real key for forming plate tectonics on Earth. All right, so then when we start thinking about the early Earth, we need to really open our minds to different kinds of tectonic regimes, because we don't know if these processes that form plate boundaries on the Earth are going to work at early Earth conditions. Okay? So if we can't form these weak plate boundaries, then we're going to be stuck in a different kind of tectonic regime, likely a stagnant lid regime. Right? So in a stagnant lid, instead of the lithosphere being broken into these discrete plates, right, that can move around, and you've got these weak plate boundaries allowing that motion to happen, we can't form weak plate boundaries at all. We can't really form any plate boundaries. So the whole lithosphere is just one rigid plate covering the entire surface of the planet, right? So that means it's also basically immobile. There's no subduction, right? We don't have these surface rocks diving down into the interior, right? And there's no effective plate motion at the surface. That doesn't mean that nothing is happening on these stagnant lid planets. They're not just geologically or tectonically dead, right? Stagnant lid planets still can certainly have volcanism, especially early on in their histories when there's more heat sources from radioactive elements powering melting and tectonism. So there can still easily certainly be volcanoes and lava flows at their surface. This surface volcanism can also potentially provide at least some sort of slow, probably less effective recycling of volatiles to the interior, right? So as lava flow erupts at the surface, rocks there can still interact with volatiles at the surface, just like the ocean crust and the crust on Earth does. And then as later lava flows erupt and form, the surface rocks get buried down through the lithosphere on a stagnant lid planet. And if this happens enough, right, you can potentially get rocks that were at the surface interacting with volatiles all the way down towards the bottom of the lithosphere, where they might be able to kind of blob off into the mantle, right? The process we call foundering of the lithosphere or delamination, like this cartoon showed, or this cartoon names it. Right, and then a third regime that's worth highlighting is a situation where a planet switches back and forth between these two, stagnant lid and plate tectonics, and that's called an episodic regime, right? In an episodic regime, we generally see a pretty long period of stagnant lid behavior, often on the order of 100 million years or more, right? That then gets all of a sudden interrupted by a short and really rapid burst of subduction that covers basically the whole planet, right? So subduction zones form, and then the whole lithosphere subducts and gets recycled into the interior on a short time scale. It can be just a few millions of years or tens of millions of years, right? So this episodic behavior, right, we tend to see stagnant lid for a long time, and then a huge resurfacing subduction event, and then back to stagnant lid behavior for another long period. Okay, so we know we've got these different regimes, right? So we want to think about, whether there are reasons to think that the early Earth might not have been in a plate tectonic regime, right? And in fact, there are, and I'll highlight a couple reasons that have been proposed for why the early Earth might have been less conducive to forming plate tectonics than the modern Earth. Right? So one of these ideas is that, first of all, the mantle was almost certainly hotter in the past than it is today. There was more production of heat by radioactive elements. There's also more primordial heat from formation and from giant impacts like the moon forming impact that was left behind at that time. Right, so we expect higher mantle temperatures in the early Earth, Hadean and Archean period than we have today. These higher temperatures we found in geodynamic models tend to reduce the stresses that convection is applying to the lithosphere. Right? And the reason for that is the viscosity of the interior gets much lower, right, as a result of these higher temperatures. So you've got this lower viscosity fluid kind of dragging on the lithosphere above, right, and that reduces the stresses the lithosphere feels. All right, then if we think about the way to make plate boundaries as being essentially breaking or fracturing the lithosphere, right, that's a process that depends on the stress, right? Basically, there will be a certain strength of the plates, right, which is called the yield strength, right, that we need to reach in order to make the plate break and form a plate boundary, right? So if the stresses that convection is applying to a lithosphere are getting smaller and smaller as we make the mantle hotter, then it's going to be harder and harder to reach this yield strength and make plate boundaries and make plate tectonics, right? So there's been some geodynamic work showing this effect, where as you increase the internal heating rate, right, making the planet hotter, right, stresses are going down, right, and a planet can transition from a mobile lid, right, or plate tectonic state into an episodic or maybe even a stagnant lid state, right? I want to highlight that this effect is dependent on the mechanism that's being assumed for forming plate boundaries. And if we use a different mechanism, again, we don't know what the right mechanism is, then we can get different behavior. So I've done some work where we use grain size reduction to make weak plate boundaries. And with that mechanism, increasing the mantle temperature actually does not cause the same switch to a stagnant lid, right? So, we can't really say one way or the other and need to keep our minds open to different possibilities for the tectonic state. Right, another reason that we can't just assume plate tectonics was happening with no problem on the early Earth, right, is the buoyancy of plates, right? And as the mantle gets hotter, it turns out that it tends to make a ocean plate, right, which are the plates that are capable of subducting and really driving plate tectonics, tends to make those plates more buoyant and harder for them to sink down into the underlying mantle. Right, the reason for this is every oceanic plate is made up of a layer of crust, right? And the crust is less buoyant than or the crust is less dense, I should say, than the mantle rocks beneath it. And then there's a layer of cold mantle lithosphere beneath the crust, right? And that mantle lithosphere, because it's cold, is now more dense than the warmer mantle rocks beneath it. So to get a plate to be negatively buoyant and able to subduct, we need that mantle lithosphere layer, right, to be thick enough that it overcomes the positive buoyancy of the crust. When the mantle temperature gets higher, we expect higher rates of volcanism and therefore a thicker crust, right? The crust could be up to 20, 30 kilometers thick. And again, this is the oceanic crust rather than continental crust, right? So that means we would need an even thicker lithosphere to counteract that positive buoyancy. At the same time, as the mantle temperature is higher, convection in the mantle tends to be faster and more vigorous, and that can actually make it harder to form a thick, cold layer of mantle lithosphere beneath the crust, right? So it's possible that going from lower temperatures in the mantle, right, to higher temperatures, right, would make it so that plates are unable to become negatively buoyant and unable to subduct, right? Again, there are details that can change the story and get around this problem, right? But for our purposes, we should take this as reasons to not just blindly assume that there was always plate tectonics as we go back in time, and that there could have been a range of tectonic processes from stagnant lid to episodic to maybe modern style plate tectonics operating deep in the past. All right, so what do these different tectonic regimes do for volatile cycling, right? And how do they influence atmosphere evolution? All right, so first we're gonna talk about CO2 cycling, and first focus on plate tectonics and look at the kind of fluxes of CO2 from the interior to the surface and back again, right? So CO2 can be released from Earth's interior, right, to the surface in a process we call outgassing or degassing, right? And it's generally tied to volcanism, right? So there's CO2 stored in various mineral phases in Earth's mantle, and that's released to the atmosphere and oceans, right? Released really to the surface environment, we should say, through volcanism at mid-ocean ridges, right, where plates spread apart. Volcanism at ocean islands like Hawaii, where we think there are upwelling plumes of hot mantle coming from deep in the interior that rise up to the base of a plate, cause melting and volcanism there. Both of those take CO2 that was stored in the mantle in some way and release it to the atmosphere and ocean environment. The other main degassing or outgassing flux, right, is carbon that gets stored in the ocean crust on an oceanic plate, that then subducts down into the interior, heats up, and this process of going to higher temperatures and pressures causes the minerals that are carbonate minerals that are storing CO2 to break down and release a lot of the CO2 back to the atmosphere, right? So the way this happens is this CO2 and other fluids, water plays an important role. This are released from the plate that causes melting, right? This melt eventually makes it up to the surface in the form of arc volcanoes that form subduction zones, right? And then these volcanoes release those volatiles back to the atmosphere. Right, CO2 comes out of the atmosphere back to the plate surface, right, through weathering. Right? And weathering and the carbonate silicate cycle was covered in one of the earlier talks. Right, so weathering removes CO2 out of the atmosphere with reaction to rocks on the surface. Right, these weathering products flow into the ocean and form carbonate rocks, carbonate minerals on the seafloor that are then subducted. Right, the other process is hydrothermal alteration, right, which you can think of as the same kind of weathering process, but happening directly on the seafloor and forming carbonate minerals directly in the ocean crust, right, through fluids circulating through the ocean crust there, right? And when these carbonate minerals are subducted, right, like I said, some of them are lost, right, through these metamorphic reactions and come back up arc volcanoes. The amount that remains, right, and isn't lost from the downgoing plate will be recycled into the deep mantle. All right, so what does this mean for climate evolution, right, and the evolution of the carbonate silicate cycle, right, as Earth evolves over time? right, so we already said that the early Earth was likely hotter, right? And we think the Earth has probably generally been cooling over time as a result of heat loss from the interior to the surface and the decay of radioactive elements in the interior. Right? So a hotter mantle is generally going to lead to more vigorous convection, right? So if there was plate tectonics, you generally expect plates to be moving faster, although there's some arguments about that when we go into the details. And in general, that's going to then lead to higher rates of volcanism and therefore higher rates of volcanic outgassing of CO2 and other volatiles, but we'll focus on CO2 now, to the atmosphere. Another important effect here is that when the mantle is hotter, that makes it easier for volatiles to come off a subducting slab, right? And harder for volatiles to be retained in that slab all the way down into the mantle interior, right? So that's also generally going to lead to higher rates of outgassing from the subducting plates, right? Coming out arc volcanoes. At the same time, we're also getting higher rates of outgassing from, say, mid-ocean ridges and ocean islands, right? So in general, the hotter the mantle, it's probably going to be harder to recycle volatiles back into the interior, and we're going to have more volatiles sitting in the surface environment in the ocean and atmosphere reservoirs. And so this modeling work from Tachika and Matsui, where they combined mantle evolution and the carbonate silicate cycle in some really nice papers from the early 90s, they estimated that the volcanic outgassing flux from mid-ocean ridges, that's this VD, right, might have been 10 to maybe even 100 times higher in the Hadean and Archean versus today. All right, this is generally good news for things like the faint Youngstown problem, right? So at the same time that we have lower solar luminosity, right, we're also most likely going to have higher rates of outgassing, helping put more CO2 in the atmosphere and counteract the effects of the lower luminosity, right? So higher outgassing plus combining with this thermostat effect that comes from silicate weathering is good news for helping solve the faint Youngstown problem, right? Of course, you saw more detail on this in one of the earlier talks. You know, there's probably other greenhouse gases that really help solve this problem, but the evolution of the interior plays some part. Okay, there are a lot of arguments and complications about this kind of story, and I don't want you guys to think that, you know, what I showed in those first couple slides on this is the, you know, definitive word on this topic. Right? So one is the thermal evolution of the Earth, basically how the mantle temperature has evolved over time, is not something that we understand very well. And so the modeling I showed earlier takes the kind of traditional view, which is shown in this dashed black line here, that the early Earth started much hotter, cooled very rapidly, and then the mantle temperature has been cooling more gradually today. Right? But there are alternatives that have been proposed based on some issues with Earth's present day heat budget, that instead of this rapid cooling and then slower cooling, the early Earth might have been cooling less slowly or maybe even heating up and then cooling more rapidly onto today. Right? And these different kinds of temperature evolution trends would lead to different, in the details, outgassing rates and carbonate silicate cycle behavior in the early Earth. But in general, we would still pretty much expect higher outgassing rates in the past. It's also possible, and we'll talk about this in more detail a little later in the talk, that the area of exposed land might have been much smaller. This is going to limit the amount of silicate weathering that can happen on land, right? And so the removal rate of CO2 from the atmosphere by that weathering process. But it turns out that with some recent work now showing that seafloor weathering can act as a major climate stabilizer, right? And produce the same kind of climate buffering effects that silicate weathering and thermostat effect, I should say, silicate weathering on land does. That's probably not a big deal if there was very little exposed land on the early Earth. You know, it seems likely, at least based on what we know now, that seafloor weathering could serve the same role and still help keep the early Earth climate temperate and habitable. Maybe a bigger effect, and Kevin Zonley might touch on this a little more in his talk, is impacts, right? So when there's a large impact coming in, spraying this ejecta out through the atmosphere on the surface, right, that ejecta can weather really easily, right? And that can really enhance effective weathering rates, draw lots of CO2 out of the atmosphere, and potentially lead to cool climates, right? So the effective ejecta could even really overwhelm this effect of higher outgassing rates from a hotter mantle. Right, so those are ideas about how this happens on a plate tectonic planet. If instead we had a stagnant lid planet, there is still a type of CO2 cycling that develops, and it can still play some of these same roles in regulating the climate on the planet. Right, so CO2 will still be stored in the mantle, and volcanism in the mantle, right, which will happen certainly on stagnant wood planets, just like it happens on the Earth, could release this CO2 to the atmosphere, right, and provide a outgassing rate that helps keep the climate from freezing over, right? As long as we have water on the surface, right? So if we're thinking about the early Earth, if it was maybe in a stagnant lid regime, then we know there is still water on the surface. So that means weathering can still happen, right? Draw CO2 out of the atmosphere and also give us this stabilizing thermostat effect. Right. One interesting difference, though, with a stagnant lid planet is whether we can recycle this carbon all the way back into the mantle or not. Right. And on a stagnant lid planet, we probably can't get it all the way back to the mantle. It's probably going to mostly stay in the crust. Right. So when volcanic eruption happens, right, and then weathering deposits some carbon from the atmosphere into the crust, later lava flows, all right, will bury that carbon down through the crust. All right. And it turns out that in pretty much all cases, before that buried crust would reach the bottom of the lithosphere, right, and be recycled into the mantle, it reaches temperature pressure conditions where metamorphic reactions, just like in subduction zones, kick in and we'll want to release that CO2 back to the atmosphere. Right? So on a stagnant lid planet, we lose CO2 from the mantle to the surface, and then it kind of just recycles in the crust, right, for as long as volcanism is active. All right, we get some of the same feedbacks that I mentioned, that I kind of touched on in the previous slide, that will help regulate climate, right? We're going to still have higher outgassing rates early on in the planet's history when the mantle's hotter. That helps lead to higher amounts of CO2 in the atmosphere and keeps the climate potentially warm, possibly enough to counteract the faint young sun problem. As a stagnant lid planet evolves, right, and cools off, its rates of volcanism and outgassing are going to go down. Right? That's going to cause the CO2 in the atmosphere to drop and the surface temperature as well. And eventually it kind of falls off a cliff here, right? And that's when the planet essentially becomes volcanically dead, right? Eventually it's going to cool off to the point where there's no more volcanism and outgassing, right? And this will probably plunge the planet into a frozen snowball state. This probably wouldn't happen for 2 billion years or more on an Earth-like planet. So if the early Earth was in a stagnant lid regime, right, there's plenty of time for it to transition to plate tectonics before getting stuck in this frozen state. But this might be important for exoplanets if they always stay in a stagnant lid regime. All right, what if we had an episodic regime? This is something that is not well studied in terms of what the climate state or climate evolution would look like in a real episodic regime with a long period of stagnant lid behavior and then a rapid subduction. But what there has been some work on is the climate signal of forming a new volcanic arc at a new subduction zone, and then having that volcanism die out, right? And so what's been found here is that when the new subduction zone and volcanic arc is forming, right, there's a big increase in the outgassing rate as we're forming all these new volcanoes and releasing a bunch of volatiles or a bunch of CO2 coming off this downgoing plate, right? And this is overwhelming any effect of weathering. And so we end up with a CO2 source, right? So early on when subduction is starting, we'd expect a warming signal, right? Then when the subduction zone dies out and its volcanism dies out, what's left behind are big mountains, right? Like the Cascade Mountains or the Andes or things that form, that we know form in subduction zones, right? And with tall mountain topography, we have high erosion rates and high weathering rates. Right, so with the CO2 source from subduction shut off, right, now we have active weathering from all this topography, and we end up with a net CO2 sink that can last for tens or even hundreds of months, or I should probably say tens to up to maybe an order of 100 million years until this topography gets wiped out. So an episodic regime might go through these cycles of warming, right, when subduction initiates, and then slow cooling when subduction has died down. Right? More work is needed on that. Okay, what about water cycling? And this really gets into then thinking about whether we would expect there to be a significant amount of land exposed or not at the surface of the Earth during the Hadean and Archean. All right, so I mentioned earlier that a hotter mantle is going to make it harder for volatiles, both CO2 and water, to make it down into the mantle interior before they're lost, right, through metamorphic devolatilization reactions in the slab and released back to the surface through these volcanic arcs. All right, so here's a modeling result showing this. So this is the amount of water retained in the slab. Warmer colors means more water retained. Blue, dark blue means nothing retained, as a function of the subduction velocity and the plate age, where older plate means thicker plate. All right, so at conditions like today, pretty fast, old plates can recycle a lot of water into the interior. If we make the mantle hotter, like the temperatures that prevail in the Archean, right, then it's much harder to recycle water into the mantle. Almost none of the subduction speeds and ages, considering that study, would take much water into the mantle, right? There's also geochemical evidence for this based on looking at noble gas tracers, which tell us about volatile cycling processes, that the Earth might have been overall outgassing volatiles like water before 2.5 billion years ago, and then started ingesting water and other volatiles in the interior, right? So all these point to the idea that there might have been more volatiles sitting at the surface, right, rather than the interior and the early Earth, right? So we might expect the ocean volume to have been larger in the past than it is today. All right, another important constraint that then comes in for helping us think about how much land might have been exposed on the early Earth, right, is thinking about how large the volume of ocean basins would have been, right? So one, right, the effect of a hotter mantle on subduction means that there was probably more water in terms of a total mass or volume of water sitting at Earth's surface. Even if you don't take that into account, and we have the same amount of water on Earth's surface, right, ocean basins themselves were probably shallower, and that would push the sea level up and flood more of the continents and land in Earth's past, right? So this figure is showing models for what the distribution of topography would have looked like on the modern Earth, right? That's the gray curve. That's something we can measure pretty well. And these low topography, negative topography regions are the seafloor, right? Above the higher topographies here is the continents going up to then tall mountain ranges. Right, in the past, the continental coverage might have been less continental material around, but the seafloor, right, we think might have been higher. And the reason for that is, again, this issue of plate buoyancy. We had a thicker crust, right? The lithosphere, mantle lithosphere beneath the crust might have been thinner. All of these effects come together to make plates float up a little higher on the mantle, right? And have a shallower topography, or maybe I should say shallower bathymetry than they have today, right? So if the ocean basins are smaller, right, water's getting pushed up, the sea level is getting pushed up, and more land's being flooded, right? So taking these effects into account, we easily could have had maybe 10% or less, maybe even just a few percent of Earth's surface area actually exposed above sea level versus submerged below water, right? So the early Earth might have looked something like this, with just tall mountains sticking up above sea level, and then even whatever continents were present might have been mostly submerged, not really emerging above sea level till possibly later in the Archean or the end of the Archean. All right, the same story probably holds if there's a stagnant lid on the early Earth rather than plate tectonics. We don't know as much, right? Or actually, we really know a lot less about water recycling with a stagnant lid compared to plate tectonics. But generally speaking, it's probably even harder to take water from the surface down into the interior with a stagnant lid. So you'd probably expect even more water at the surface on a stagnant lid planet. Essentially, if the early Earth was in a stagnant lid regime, the amount of water at the surface might have been even more than what we would have with plate tectonics, right? And the reason for that is, so this is showing where basaltic oceanic crust can store water versus not store water. So it can stay hydrated for these temperature pressure conditions, and it loses its water for these temperature pressure conditions. Subducting slabs on the modern Earth follow a geotherm, a temperature pressure profile, something like this, so they can keep their water to great depth. But if we didn't have subduction, and the only way we could get surface rocks down to the interior was this volcanic burial process, right, then these rocks are going to experience a much higher temperatures at shallower depths following this is just a schematic I drew on here, but a geotherm like this, right? So they're much more likely to lose their water before reaching depths or pressures of the mantle interior and recycling this water. Right, so if the Earth was in a stagnant lid, right, there's probably more water at the surface, right? It's also going to be very difficult, maybe impossible to form continents, right? So the only real hope for forming land that could be exposed above surface are big hotspot volcanoes like Hawaii, right? Or an example in the solar system is Olympus Mons on Mars, which is probably a big hotspot volcano. But these can grow really big. Olympus Mons is the biggest volcano in the solar system, right? So I think it's quite possible, probably even quite likely, right, that these hotspot volcanoes could still grow large enough to stick up above sea level on a potentially stagnant lid early Earth. And in fact, even if there was plate tectonics, hotspots like this might have still been the best bet, given the fact that continents might have been more submerged to create land exposed above sea level, right? So there was probably less exposed land, but I would be very surprised if there was no exposed land at all, right? There are reasons why we should expect at least some mountains to form that could stick up above sea level. All right, so in summary, tectonic processes that prevailed on the early Earth are highly uncertain, right? But despite this, we can be pretty confident that whatever tectonic regime prevailed was probably able to drive at least some form of volatile cycling and carbonate silicate cycling, right? And probably still able to provide these kind of climate stabilization, climate regulating effects, right? A hotter interior is likely to lead to higher rates of volcanic outgassing for pretty much any volatiles. I focused on CO2 and water. All right, this is going to at least play some role in helping solve the faint young sub problem. I won't say it solves it definitively, but at least helps. And it also means that there's probably a larger volume or mass of water at the surface in the past than there is today. At the same time, ocean basins might have been shallower due to the buoyancy of plates we would expect on the early Earth, and that further acts to raise sea levels. So summing that together to think about the area of exposed land, it was probably much less in the Hadean and Archean than today, maybe even just a few percent of Earth's surface, or even potentially lower, was exposed land. But I doubt that there would have been no exposed land at all, right? And in different tectonic regimes, plate tectonics or stagnant lid or episodic regimes, there's still going to be ways to form mountains that could grow tall enough to stick up above sea level, right? So those kinds of mountain chains might have been the best bet to have exposed land in these wet, dry cycles that might be important for the origin of life. Right, thanks.